Welcome back to AI Paper Podcasts. Today we're diving into a really interesting paper called Bridging Continuous and Discrete Tokens for Auto-Regressive Visual Generation.
Yeah, this one comes from researchers at the University of Hong Kong, ByteDance, École Polytechnique, and Peking University.
And it tackles a core dilemma in AI image generation. Do you use discrete tokens? They're simple to model, but you can lose information, get instability.
Or do you go with continuous tokens? Much better detail, but way more complex to actually model step-by-step auto-regressively.
Exactly. So this paper introduces TokenBridge. And the key idea is pretty neat. They use post-training quantization.
So they take a pre-trained and continuous model like a VAE, get those rich features,
and then turn them into discrete tokens afterwards. So you kind of get the best of both, detail and simpler modeling.
That's the goal. So for the quick version, if you're just tuning in, TokenBridge takes continuous VAE features, uses this clever dimension-wise quantization to make discrete tokens, and then predicts them auto-regressively channel by channel.
Right. Efficiently handling a potentially huge token space and getting high-quality images using standard categorical prediction. No complex diffusion needed for the generation part.
Okay, so let's unpack that a bit more. This whole field of auto-regressive visual generation. It's basically like language models, right? Predicting the next piece.
Yeah, exactly. Instead of the next word, you're predicting the next visual token, the next patch of the image based on what you've already generated.
And central to this is the image tokenizer, the thing that breaks the image down into those tokens.
Which brings us back to that discrete versus continuous split.
Right. Autoregressive models are super promising, especially for multimodal stuff and leveraging all the LLM progress.
But this token representation thing has always been, well, a bit of a headache.
Let's talk about the traditional discrete ways first. The paper mentions methods like VQ, VAE, or LFQ.
Right, vector quantized VAEs. With these, the quantization, that step of making things discrete, happens during the tokenizer training itself.
Yeah, it's baked in. And technically, that's tricky because quantization isn't differentiable, like rounding a number.
Ah, the classic gradient problem. Tiny input change doesn't always change the output, so backpropagation gets difficult.
Exactly. So you need workarounds, gradient estimators, things like the straight-through estimator.
Yeah.
And that can just make the training a bit unstable.
Okay, so that's one issue. What's the other one they mentioned?
It's the trade-off between your vocabulary size, how many different discrete tokens you have, and the level of detail you capture.
Makes sense. Small vocabulary, you lose detail because each token covers too much.
But if you make the vocabulary massive to try and capture everything,
You end up with tons of codes that barely ever get used.
precisely, poor codebook utilization. It's inefficient and can actually make it harder for the main model to learn useful patterns.
Okay, so challenges on the discrete side. What about going fully continuous with something like a VAE?
Well, the big plus for VAEs is they learn this really nice, smooth, continuous latent space. Captures tons of detail.
And because it's continuous, training is smoother. Standard backprop works.
Yep, direct gradient flow helps preserve all that fine-grained information. No quantization bottleneck during the tokenizer training.
Sounds ideal. So what's the catch for building auto-regressive models then?
The catch is that your standard autoregressive models, like the ones used in NLP, they're built to predict discrete categories.
Yeah.
Pick one word from the vocabulary.
Right. They output probabilities over a fixed set of items.
But continuous tokens don't fit that mold. They're, continuous values, so you can't just slap a standard softmax prediction head on top.
So you need different techniques. The paper mentioned things like diffusion models or Gaussian mixture models.
Exactly. You need ways to model the probability distribution of those continuous values. And that often means more complex architectures, maybe iterative sampling like in diffusion.
Which makes the whole generation pipeline slower and more involved.
Right. So great detail from continuous tokens, but complexity in modeling them auto-regressively.
Okay, so that really sets the stage. Discrete, simple modeling, info loss, instability, continuous. Great info, complex modeling.
And this is where TokenBridge comes in as the, bridge.
The core idea sounds simple enough. Decouple discretization from the initial training.
Yeah. Train a good continuous VAE first. Let it learn to represent images really well.
Capture all that detail.
Then, after that VAE is trained, figure out how to turn those continuous features into discrete ones. Post-training quantization.
So you're hoping to keep the representation power of the continuous space,
but gain the modeling simplicity of discrete tokens for the actual generation part.
Okay, let's get into the specifics. This post-training dimension-wise quantization. How does that actually work?
So you start with the continuous latent features from your pre-trained VAE encoder. Let's say you have a feature map with C channels.
Okay.
Now, just doing standard vector quantization on the whole vector across channels, it's not tough. To keep the detail, you'd need a massive codebook. Think B levels per channel, C channels. That's B to the power of C possible codes.
Whoa. Yeah. Exponentially huge. Impractical.
Totally impractical. So instead, they quantize each dimension, each channel, independently.
Ah, okay. Dimension-wise. So you only need B codes per dimension.
Exactly. You avoid that exponential blowup. This lets you use a reasonably fine quantization, say B64 levels, for each channel without needing an astronomical codebook.
Clever. And they leverage some properties of those VAE features.
Yeah, two key things. First, VAE training usually involves KL divergence loss, which encourages the latent features to be somewhat bounded and often kind of Gaussian-like.
Right, often close to a standard normal distribution.
So they use that. They figure out the practical range of the features, say from alpha min to alpha max, and normalize them, maybe to AR.
Okay.
Then instead of just dividing that range linearly, they look at the standard normal distribution and divide it into B bins, where each bin has the same probability mass.
That's smart. So you get more resolution where the values are more common, near the mean of the Gaussian.
Precisely. More efficient use of your quantization levels. Then, for each of these probability-based bins, they calculate a representative reconstruction value.
Like the center or average value within that bin's probability range.
Something like that, yeah. The expected value within that interval of the standard normal distribution mapped back. So now you have B discrete levels, each with a reconstruction value.
Got it. So a continuous value comes in, gets normalized, find which bin it falls into based on those probability boundaries.
Find the closest reconstruction value and assign the index of that bin. That's your discrete token for that dimension.
Okay, that makes sense. And then to use the VAE decoder, you need to go back to continuous. Dequantization.
Simple enough. You take the discrete index, map it back to its corresponding reconstruction value, and then unnormalize it back into the original feature range.
And that continuous-ish value can then be fed into the pre-trained VAE decoder.
Exactly. It allows them to leverage that powerful pre-trained decoder with minimal changes. They also mentioned that even simple linear quantization works okay if B is large enough, but this probability-based approach is more efficient.
Okay, so they've got their discrete tokens, one for each dimension. Now, how do they predict these auto-regressively? Because, as you said, B to the C is still a huge potential combination space for the full token at one spatial location.
Right, and simply predicting each channel's token independently in parallel. They tried that. Doesn't work well.
Why not?
Because there are crucial dependencies between the channels. Think about it. Different channels likely encode related aspects of the image patch, like color and texture. You need to model that relationship.
Makes sense. So parallel prediction is out. What do they do instead?
They use a lightweight autoregressive head, but it operates across the channel dimension.
Okay, wait. So for one spatial patch, they predict the channels one by one.
Exactly. Predict the discrete token for channel 1. Then, using that predicted value and the context from the main model, predict the token for channel 2. Then use channels 1 and 2 to predict channel 3, and so on for all C channels.
Ah. So it's auto-regressive within the channel dimension at each spatial step.
You got it. It models the joint distribution P token context by breaking it down into P channel 1 context, P channel 2 context, channel 1, channel 2, and so on.
That neatly decomposes the huge classification problem into C smaller classification problems, much more manageable.
Way more manageable. And crucially, it captures those inter-channel dependencies that parallel prediction misses.
And they even optimize the order they predict the channels in. Something about frequency.
Yeah, another clever touch. They analyze the channels using FFT to see which ones carry more low-frequency information, the broader structure.
And they predict those first.
The idea is to generate the overall structure and coarse details before moving on to the finer, high-frequency details, like sketching before shading. It gave them a small but consistent boost.
Cool. So putting it all together in the main generation framework, how does it flow?
Okay, so you have your main autoregressive backbone, like a transformer, working spatially across the image patches.
Providing context based on previously generated patches.
Right. At each new spatial location, the backbone outputs some context features. These features are fed into that shared, dimension-wise autoregressive head we just discussed.
Shared across all spatial positions, right, to save parameter.
Exactly. And that head then sequentially predicts the discrete token for each channel, C times.
Using standard cross-entropy loss for training on each of those C predictions.
Yep, straightforward training. Then during inference, same process. Backbone gives context, head predicts channel 1, then channel 2, using channel 1's prediction, and so on.
And once they have all C-channel tokens for a spatial location.
Crucially, they immediately dequantize that full token back into a continuous feature vector.
Ah, right. To feed it back into the main backbone as context for predicting the next spatial location.
Exactly. This keeps everything flowing within the VAE's learned latent space, even though the prediction target was discrete. It connects the discrete prediction back to the continuous representation space.
That seems like a really key detail. Okay, let's talk results. How well does this actually work? They looked at the tokenizer first, right? Reconstruction quality.
Yeah, they compared TokenBridge reconstruction against the original continuous VAE and also against traditional discrete methods like VQGAN and LFQ.
And TokenBridge held up well.
Very well. Figure 5 shows it. It was almost identical to the continuous VAE in reconstruction quality and noticeably better than VQGAN and LFQ, especially on tricky details like text or faces.
So the post-training quantization didn't hurt the VAE's representational power much?
Apparently not, especially with enough quantization levels. They tested different numbers of levels B.
What did they find there? Table 1A, I think?
Yep. As you'd expect, more levels, finer quantization meant better reconstruction. With B64, they basically matched the continuous VAE. Figure 6 shows this visually too.
And they also checked the quantization range, alpha min, alpha max.
Right, table 1B. They found that quantizing within about ±5 standard deviations worked great, capturing most of the near-Gaussian feature distribution. Didn't need to capture extreme outliers.
Okay, so the tokenizer part seems solid. What about the generator itself? That parallel versus auto-regressive channel prediction.
Big difference there. Table 2A and figure 7 really highlight it. Parallel prediction was blurry, kind of garbagey. The dimension-watch auto-regressive prediction was much better.
Really confirming that modeling those inter-channel dependencies is vital.
Absolutely essential.
And the frequency-based dimension ordering, did that help generation much?
It gave a slight edge, yeah. Table 2B shows a modest but consistent improvement in metrics like FID when using the frequency ordering. So structure first helps.
Okay. And more quantization levels, be improved generation too, like reconstruction.
Yep, Table 2C shows consistent gains in FID and IS as B increased. Finer quantization helps both representation and generation.
They also tried grouping channels, right? Predicting multiple channels at once.
Yeah, Table 2 and kind of counterintuitive. It actually made things worse, even though it used more parameters.
Why do they think that happened?
They suggest it might just make the classification task too hard. Predicting 1 out of B squared or B cubed classes is tougher than predicting 1 out of B classes C times.
Makes sense. And the head architecture, did it need to be huge?
Table 2E shows that even a lightweight head worked reasonably well, but increasing its capacity did lead to better results, as you'd probably expect.
Okay, one interesting thing they mentioned was confidence-guided generation. How does that work?
Yeah, that's a neat benefit of having discrete predictions, since the model outputs probabilities for each discrete token choice for each channel.
You know how sure it is about its prediction?
Exactly. So you can set a threshold. Only accept and generate tokens where the model's confidence, the predicted probability, is high.
What does that achieve? Figure 8 showed some examples.
It tends to generate cleaner foreground objects against a simpler or even omitted background. It could be useful for things like transparent generation or maybe compositional generation, focusing only on the high certainty parts. Not as easy to do with continuous outputs directly.
Cool side benefit. Okay, the main event. How does TokenBridge stack up against other state-of-the-art methods on ImageNet? Table 3.
Right. They compared their models, ours L and ours H, large and huge presumably, against both discrete and continuous methods.
And against other discrete methods.
They generally got better FID scores, often with smaller models too. So the post-training approach seems more effective than training time quantization methods like VQGAN variants.
And against continuous methods, things like GGuiVT or Flower.
They also outperform those, again, sometimes with fewer parameters.
The big comparison seemed to be against Merar, which uses diffusion for continuous tokens.
Yeah, that's a strong baseline. Their ours H model achieved a similar FID to MRH.
But better on other metrics.
Right. Better inception score, IS, and recall, with slightly fewer parameters than MARH. And importantly, TokenBridge uses simple categorical prediction, while MA uses complex diffusion sampling.
That's a pretty significant achievement, getting comparable or better results with a much simpler generation mechanism.
It really does seem like they successfully bridged that gap.
And for people wanting to implement this, the appendices have details.
Yeah, Appendix A gives the nitty-gritty. ImageNet training, the specific VAE they used, B64 levels, the architectures for their L and H models based on MAO's backbone, head dimensions, training details like classifier-free guidance. Table 4 has hyperparameters.
And speed. That's often a killer for complex models. Appendix B.
Big win there too. Table 5 shows their dimension-wise prediction is almost 6 times faster than MAR's diffusion sampling for generation.
It's 6 times because it's direct prediction, not iterative refinement.
Exactly, you just do C prediction steps per spatial location. They also note that newer VAEs are using fewer channels, smaller C, which would make TokenBridge even faster.
Nice. Any limitations mentioned? Appendix C.
Main one is obvious. The performance is tied to how good your initial VAE is. Garbage in, garbage out, essentially.
Makes sense. It builds on the VAE's representation.
They also talk broader impacts, hoping this encourages simpler designs, maybe helps unify multimodal modeling since text is already discrete, and the usual caveats about potential misuse of generative models.
Standard responsible AI points. Okay, so wrapping this up, TokenBridge seems like a really elegant piece of work.
I think so. Post-training quantization plus that dimension-wise autoregressive head, it hits a sweet spot.
High-quality results, rivaling complex continuous methods, but using standard, simple cross-entropy loss and categorical prediction.
Yeah, it shows you don't always need the most complex machinery for top results. Sometimes bridging existing ideas in a smart way is incredibly effective.
Definitely. So for you watching, the provocative thought maybe is, where else could this idea of bridging representations apply? We often see these trade-offs between complexity and performance.
Right. Could similar post-hoc discretization or dimension-wise modeling simplify things in other domains like audio, video, or even beyond perception tasks?
And what does it mean for efficiency and accessibility if we can achieve great results with simpler, faster models? Lots to think about. Definitely check out the paper for the full details.
Yeah, well worth the read.